the first author of this paper. However, due to a very happy reason, his wife is about to give birth to their child, so he couldn't travel to attend the conference. I'm excited for Menghao's growing family, so on his behalf, I will be presenting our work today. My name is Guanyu Li, currently at Huawei, and this work was done in collaboration with Menghao during my PhD studies in Tsinghua University. It's my honor to be here to introduce our work, SuperFE, a scalable and flexible feature extractor for ML-based traffic analysis applications. Let's start this talk with traffic analysis. Traffic analysis refers to a class of application that infer sensitive information to identify malicious behaviors from network communication patterns. By using traffic analysis applications, a network operator can identify the botnet compromised and controlled by attackers, pinpoint individuals engaged in illegal activities within privacy technologies such as Tor, detect cover channel attacks that exfiltrate confidential information from compromising machines, and prevent malicious activities that intrude the network. Today, traffic analysis applications are transitioning to use machine learning, especially deep learning, to achieve superior accuracy. In a common traffic analysis application, there are usually two typical components. One is a feature extractor component that extracts necessary traffic features in the form of feature vectors from raw network traffic. The other one is a behavior detector component that leverage machine learning algorithm to detect the desired network behaviors. For example, in Keysun, a neural network-based network intrusion detection system, there is first a feature is extraction component, which extracts 115-dimension traffic feature vectors, followed by an example of autoencoders, which takes feature vectors as input to detect abnormal packets. However, as the network traffic is reaching multi-hundred gigabytes per second recently, feature extractor in today's ML-based traffic analysis applications are becoming a key bottleneck. Software feature extractors usually use port mirroring to duplicate collected network traffic and leverage a set of servers to store large volumes of network traffic and extract the desired traffic features, which usually incurs substantial communication, storage, and computation overheads. Some recent works attempt to accelerate the feature extractor with specialized network hardware and implement the feature extractor, even the entire traffic analysis task in the data plan. However, restricted by the commutation model and the memory resources of the network hardware, none of them are flexible enough to support generic and versatile traffic analysis applications. We observe that the network hardware is becoming programmable, which provides an exciting opportunity to rethink the design of feature extractors. So, could we design a feature extractor that is scalable to multi-hundred gigabytes per second with low overheads, and also flexible to support generic traffic analysis applications? Our answer is yes. In this paper, we present SuperFE, a feature extraction framework that allows users to extract features efficiently and flexibly. SuperFE's improved performance and flexibility are derived from the following three key techniques. First, SuperFE presents a user-friendly and extensible interface to help users write their own feature extraction policies. Second, SuperFE introduces high-performance, multi-granularity KV vector system on programmable switches in order to batch necessary feature metadata for massive amounts of packets. And third, SuperFE designs efficient streaming algorithm-based feature computation mechanism on SmartNICs in order to fully exploit the multi-core parallelism and the hierarchical memory of SOC-based SmartNICs. First, we show how SuperFE exploits the feature extraction policies. We observe that different IML-based traffic analysis applications, they share the common feature extraction procedures. For example, selecting interested traffic, grouping traffic into multiple sites, mapping intermediate statistics, and producing and composing the final feature vectors. As a result, we adapt our SuperFE policy interface from Spark-style stream processing operators and design tuple-based packet abstraction, group-based stream processing, and efficient stream operators. These operators can be naturally partitioned across switches and SmartNICs. And deploying the first two operators, group by and filter, on the switch can significantly reduce the traffic transferred from switches to SmartNICs. Here we give a simple example, computed the mean, maximum, and minimum for the inter-packet time IPT of TCP packets for per IP host. To express this policy, we first use filter to obtain TCP packets, then use group by to group packets by source IP host, then use map to get the inter-packet time IPT, then use reduce to compute the mean, maximum, and minimum of these packets IPT. And finally, use collect to produce the final feature vector. Second, we show how SuperFE batches feature metadata on switches. Filter can be easily realized with a single match action table, matching a set of header fields and converting the predict to the rule. Group by is implemented with a novel data structure on switches, and we call it MGPV, multi-granularity grouped packet vector. Packets are grouped at the coarse granularity level, CG level, where each packet's feature record points to its corresponding fine granularity group K, FG group K. These FG group Ks are stored only once and are synchronized between the switch and the SmartNICs, from which the SmartNIC can recover grouping at intermediate granularity levels. Considering the long-tail nature of flow lengths and distributions, SuperFE adopts a hierarchical hash-based cache system to store MGPVs. It has a short buffer to store short flows, and it also prepares a stack of long buffers to catch more packets for long flows, which can effectively reduce the overall rate of messages sent from switch to SmartNIC. We also design dedicated MGPV eviction mechanism to improve the memory utilization. Third, we show how SuperFE computes features on SmartNICs. Map, synthesize, and collect usually do not involve too complex arithmetic operations and are intuitive to implement on the SmartNIC. Reduce, especially reducing functions for feature computing, are generally too computational complex to adapt to the architecture of SmartNIC, and we use a powerful streaming algorithm to implement sum, maximum, minimum, mean, variance, cardinality, and distribution-related features. We also design several optimization techniques tailored to the unique hardware architecture of SOC-based natural name NIP SmartNICs. We use hash reusing, thread switching, division elimination to optimize the computational cycles, leverage group batching and hash collision elevation to implement the group table, and resort to a hierarchical memory allocation to achieve the optimal group table placement. We implement a SuperFE prototype with Python for policy translator, P4 and C for FE switch, and micro C for FE NIC. Our test byte consists of one 3.3 terabytes per second inter-to-final switch and two Dell R740 servers as shown in the figure below. Our workload traces consist of Mingwei IXP, Enterprise, and Campus, which have different flow lengths and packet size distributions as shown in the figure. SuperFE allows concise specifications of the feature extraction policies, such as basic statistical features, packet frequency distributions, and packet direction sequence, and so on. To demonstrate the expressiveness of the SuperFE policy interface, we re-implemented the feature extractor of 10 state-of-the-art traffic analysis applications using primitives provided by SuperFE. And this table lists the lines of code allowed to implement them with SuperFE. As we can see, SuperFE is expressive and flexible to support generic traffic analysis applications. To illustrate that SuperFE is a powerful feature extractor to support traffic analysis applications, we use 4 representative applications and conduct experiments to evaluate the scalability of SuperFE integrated with these applications. The left figure shows the throughput of SuperFE with these traffic analysis applications. The middle figure shows the relative error of feature vectors produced by the original keystone and the SuperFE. And the right figure shows the detection accuracy of the original keystone and the keystone with SuperFE. As we can see, SuperFE can efficiently extract features from multi-hundred gigabytes per second raw traffic without compromising detection accuracy. To show the effectiveness of feature batching on switches, we conduct various experiments to evaluate the aggregation ratio of our new data structure MGPV, resource efficiency of MGPV, and optimization of aging design. As we can see, MGPV and aging enables effective feature aggregation with efficient resource utilization on switches. To show the effectiveness of feature computing on SmartNICs, we conduct experiments to show the memory usage of streaming algorithm, throughput scalability of SmartNICs, and optimization on SmartNICs. As we can see, streaming algorithm and resource optimizations enables efficient feature computation on SmartNICs. Okay, to conclude, feature extractors in today's ML-based traffic analysis applications are becoming a key bottleneck. We introduced SuperFE, a scalable and flexible feature extractor with a user-friendly and extensible interface, high-performance multi-granularity key vector cache system on switches, and efficient streaming algorithm-based feature computation on SmartNICs. Extensive evaluation shows the flexibility and performance of SuperFE, which empowers state-of-the-art traffic analysis applications to efficiently extract features from multi-hundred gigabytes per second raw traffic with no detection accuracy degradation, and exhibits nearly 2 orders of magnitude higher throughput than their software-based counterparts. Okay, it's all. Thanks for your attention. I'm happy to take any questions.